I'm on a little trip to Montreal, and it's the McGill University campus. Haven't been here in 3 years, and right now I'm just walking around talking to the camera like a crazy person. Do you know about the Gaia hypothesis? It was developed by James Lovelock in the 1970s along with Lynn Margulis, who is obviously famous for her endosymbiotic theory. Unfortunately, James Lovelock just passed away a month prior to filming this video. There are several versions of this hypothesis, but basically it claims that living organisms interact with their inorganic surroundings on Earth to form a synergistic and self-regulating complex system that helps to maintain and perpetuate the conditions for life on the planet. So it takes the idea of homeostasis, which is usually applied at the level of cells or organisms, but he applied it not only to the ecosystem, but to the entire planet. And the idea attracted a lot of attention, especially in the context of environmental issues. But scientifically, it's hard to test this hypothesis in any experimental setting. So a lot of people think that the hypothesis is kind of useless, but nonetheless, it's fun to think about. So in this talk, I want to introduce an idea that's also useless, but fun to think about. I want to argue that we live in a Class-4 universe. So why don't we call this the Class-4 universe hypothesis? In order to explain what I mean by that, there are a few things I need to talk about. The first thing is cellular automata. It's really simple. You have a bunch of cells that can take two states, black or white. That's where cellular comes from. And you start from the top, and the program automatically generates new patterns based on some rules. That's where the automata comes from. So the rules go like this. You have 3 cells on top, which determines what you get at the bottom. There are 2 times 2 times 2 equals 8 possible combinations of black and white for 3 neighboring cells. This rule, for example, is called Rule 30 because 11110 in binary is 30. So in total, you can have 2 to the 8th or 256 different rules. And different rules give rise to different patterns. Most are simple, repeating patterns, but sometimes you get something really interesting, like fractals. Rule 30 turns out to be very interesting. The pattern you get is completely random. There's no regularity. Take, for example, the middle column. Can we predict whether the cell will be black or white after, let's say, 1,000,000 steps? You can't. You have to run it for 1,000,000 steps to see what it is. Like the digits of pi, there are no regularities. The fact that you get complete randomness from such a simple program is remarkable. Rule 110 is even more interesting. It's Turing complete. It has the right amount of order with the right amount of randomness, which allows computation. You can tweak the initial conditions to build logic gates and perform universal computation. This is an amazing discovery. It shows how low the bar is for a system to achieve universal computation. Even a one-dimensional program based on simple rules can support universal computation. Stephen Wolfram, the guy who discovered this, classified all 256 rules according to 4 classes based on their behavior. Class 1 is homogeneous. The system settles down to either all white or all black. Class 2, you see oscillating patterns repeating itself. Class 3, random behavior with no definite structures. And Class 4, the system has both order and randomness, giving rise to complexity. Of all 256 rules, only a tiny fraction gives you complexity. And people have studied what happens to systems that are at the edge of chaos. Many claim that physical systems like the brain operates at a critical state in order to allow for stable and yet dynamic and meaningful information exchange. You can't have too much order, you can't have too much randomness. Something akin to a phase transition happens at the edge of order and chaos. Okay, now, this is the last piece of the puzzle. Okay, many physicists today believe in at least one version of the multiverse. The one that to me seems the most natural is the idea that we live in one of many universes, that outside of our observable universe, there are countless other universes that may or may not have the same laws of physics as ours. Lee Smolin, a theoretical physicist at the University of Waterloo, coined the term cosmological natural selection. It's this crazy idea that when a black hole collapses, it creates a new universe. So for every black hole, you get another universe. Information transfers from the parent universe to the baby universe. So those universes that can produce more black holes will give birth to even more universes. There you can begin to talk about the fecundity of different universes, hence the name cosmological natural selection. Absolutely crazy. No way to test this experimentally, but fun to think about. Another thing Stephen Wolfram has been working on recently is called hypergraphs. Like with cellular automata, you can generate different hypergraphs that have different rules for growth and expansion. He believes that by searching through the space of all possible combinations of rules, we can find hypergraphs that have properties that are analogous to those of our own universe. So he calls these hypergraphs different versions of universes. He already has a collection of universes that show interesting properties. He calls them the registry of notable universe models. And this is where everything comes together. Let's say we live in one of many different universes with different laws of physics. Whatever this universe generating process is, we know that we live in one that's class 4, one at the edge of order and chaos. A universe at criticality where you can form stable structures like galaxies, stars, planets, atoms, and molecules. And people talk about the anthropic principle and wonder how the universe is so fine-tuned for life to exist. But even more fundamentally, the universe is fine-tuned to have capacity for computation. The universe itself is Turing complete. If a universe had too much order and everything was uniform, you'd have no symmetry breaking, no particles. Or maybe there are universes with just repeating patterns that cannot be useful. Or the entire universe itself can oscillate between Big Bang and Big Crunch. On the other hand, some universes may have forces that are too weak to form any stable particles. Energy cannot concentrate in any meaningful way to allow computation. It's too random, always at maximum entropy. And we see this in cellular automata too. Here's research done by Melanie Mitchell at the Santa Fe Institute. They used a genetic algorithm to evolve a cellular automaton that can tell you if the starting rows of cells have majority black or majority white cells. The rule of this cellular automaton gives rise to what looks like particles, stable structures that interact with each other, and they could derive some laws about their behavior. Stable interacting structures make computation possible. And so one interesting question is, what's the percentage of class 4 universes out of all the universes? If each universe generating process is random and independent of each other, then we'll have the same probability to get each class of universes. In this case, class 4 could be very rare, as we saw with Wolfram's elementary CA. But if each generation event depends on each other, as in Lee-Smolin's cosmological natural selection, the number of class 4 universes could grow exponentially and totally overwhelm all the other classes of universes. And now I want to move on to my second idea, which is that abiogenesis, or origin of life, requires an exhaustive search of multiple universes. And for that, let me introduce the most famous cellular automaton ever created, Conway's Game of Life. And again, the rules are simple: death from isolation, survival, death from overpopulation, and birth. And this combination of rules can produce interesting patterns or life forms. Some are static, some are oscillating, and some are dynamic and complex. People love Conway's Game of Life. Many mathematicians and computer scientists have spent years looking for interesting patterns and building complex structures within the game of life. For example, this is called a glider gun. It's an oscillating structure that produces a glider every 30 generations. A glider is a moving structure or spaceship that zips across the screen diagonally. And these glider guns can be used as signals like ones and zeros. So people have made logic gates out of glider guns. This, for example, is an AND gate. And if you can make logic gates, you can build a computer within the game of life with memory, arithmetic, logical unit, and everything. Like Wolfram's Rule 110, Conway's Game of Life is also Turing complete. This means you can create Game of Life within Game of Life within Game of Life ad infinitum. And there's a wonderful concept called glider synthesis. People have tried to see if various interesting structures in Game of Life could be constructed by multiple gliders colliding sequentially from different directions, like an assembly line. This, for example, is a glider synthesis of a spaceship called 60P5H2V0. I'm pretty sure they could have come up with a better name. But look how sophisticated the synthesis is. It's truly remarkable. The Game of Life just continues to give. People have identified what they call Methuselahs from the biblical character. They are extremely long-lived structures that can persist for hundreds or thousands of generations. Take acorn as an example. This simple pattern has the potential to create wonderful structures that live on for 5,206 generations. Like the acorn in real life, so much potential packed into a tiny little seed. The acorn can be constructed using 3 colliding gliders, and there are many other such Methuselahs that have been found. Think about life in our universe. It's a hyperstructure that has persisted for 4 billion years since its birth, and it keeps on growing and evolving. So my question is, how constructible is this? How many gliders does it take to make a seed for life? One last thing I want to mention from the Game of Life. Gardens of Eve. There are patterns that have no parents, meaning it cannot arise from other patterns or the interaction of other patterns. They're not glider constructible, they cannot naturally arise. So these patterns need to occur as is from a random process. Most of these Gardens of Eden are not stable structures. They disappear eventually. But recently the community found a stable structure or still life that cannot be procedurally built. It took this community years to find the pattern. So here's my hypothesis. Something that came before Luca, that started life, whether it's per genome, collectively autocatalytic set, or RNA world, whatever you want to call it, whatever pattern that gave rise to the origin of life, what if it's a pattern that cannot naturally arise? What if there is no definite synthetic path to the seed? If you could run many universes until they die, how many universes does it take to find life? So that's why I say that life may require an exhaustive search of multiple universes, like the traveling salesman problem. There may be no shortcuts. What percentage of all universes are class 4 so you can support computation? What percentage of them will randomly come across the seed that will give rise to life? And in what percentage of those universes with life can you have something miraculous like endosymbiosis, which we know had to happen but has never been observed again? Even with all the boxes checked, you might need to be very lucky to get the correct seed. And what you really need to evolve something like this might be the ability for the system to randomly search through the space of all possibilities, quickly and continuously, to hit the correct seed. Whether the system is Turing complete or not, I think is a hardware problem. Like Wolfram's Rule 110 and Conway's Game of Life, universal computation is surprisingly easy to achieve. But whether life arises within the system or not is a software problem. For this, you might need a system that can search through a large number of initial conditions. And to me, this exhaustive search for the seed of life seems incredibly computationally expensive. A search that might require many universes. So what is the implication of all this? I like to think that we're very lucky to be here. That for us to be here to be alive and to experience life, it might have taken countless numbers of universes to test an infinite combination of initial states. And obviously at one point selection kicks in. So once chemical evolution becomes possible, the search for the seed of life becomes directed and not completely random. Even then, I suspect that there will always be an element of chance. Some key events that are going to be extremely rare, but necessary for abiogenesis. And my ideas are useless, just like many of the structures that you see in Conway's Game of Life. But they're fun to think about, and after an infinite number of those useless ideas, maybe one day we'll hit something that's really interesting.